Hello everyone, my name is Sham Parekh. I'm student of BSc Chemistry Honours first year, and today I will be reading chapter 4 Ionic Solids from the book Modern Approach to Inorganic Chemistry. So the chapter begins. Ionic solids contain an ionic bond which is formed between atoms by the complete transference of one or more valence electrons of one atom to the other atom. Therefore, in this type of bonding, one atom completes its octet and acquires noble gas configuration by losing the electrons and other by gaining the electrons. The atom which loses the electrons acquire positive charge and the other which gains the electron acquire a negative charge. These two oppositely charged species or ions come closer due to electrostatic force of attraction and form an ionic bond. Since electrostatic attraction leads to decrease of potential energy and therefore the potential energy of the system becomes less than it was before the formation of the ionic compound. The electrostatic force of attraction which holds the oppositely charged ion together is known as ionic bond or electrovalent bond. The compound containing ionic or electrovalent bond are called ionic compounds. Formation of ionic bond. An ionic bond is formed when one or more electrons are completely transferred from one atom to another atom so that both the atoms acquire stable noble gas configuration. Let us illustrate this with the formation of ionic bond by considering the example of sodium chloride, that is NaCl. Sodium atom 1s2, 2s2, 2p6 and 3s1 has only one electron in the valence shell, and by losing this electron it can acquire stable electronic configuration of neon, which is 1s2, 2s2, 2p6. On the other hand, chlorine atom 1s2, 2s2, 2p6, 3s2, 3p5 has 3p5 has 7 electron in its valence shell and needs only one electron to complete its octet. Thus, both the atoms can complete octet if sodium atom gives one electron to chlorine atom. This tendency is responsible for bonding between sodium and chlorine atoms. Therefore, sodium gives electron and becomes positively charged Na positive ion, while chlorine takes up the electron and becomes negatively charged Cl minus ion. These two ions are then held together by electrostatic force of attraction, which constitute an ionic bond. The formation of ionic bond between sodium and chlorine may be illustrated by the following electron dot picture. When atoms combine by electron transfer, the number of electrons gained or lost must be equal so that resulting compound of the whole is electrically neutral. The number of electrons gained or lost by an atom in the formation of ionic bond is equal to its electrovalency. Atoms that readily lose electrons are said to be electron positive, while those which readily gain electrons are called electronegative. Let us consider another example of calcium chloride, calcium Z30, atomic number is 30, electronic configuration is 1s2, 2s2, 2p6, 3s2, 3s2, 3p6, 4s2. Has two valence electrons and can acquire the configuration of argon by losing these two electrons. In the formation of CaCl2, the two valence electrons of calcium are transferred to two chlorine atoms, atomic number 17, 1s2, 2s2, 2p6, 3s2, 3p5, and all the ions thus formed have noble gas configurations. Schematically, the formation of CaCl2 may be represented as this. The diagram is shown in the text. Similarly, in the case of magnesium oxide, magnesium Z equals to 12, 1s2, 2s2, 2p6, 3s2 has 2 electrons in the outermost shell, and oxygen Z equals to 8, 1s2, 2s2, 2p6 has 6 electrons in the outermost shell. In the formation of magnesium oxide, both magnesium and oxygen attain the noble gas configuration by transfer of two electrons from magnesium to oxygen. The electrostatic force of attraction between Mg2 positive and O2 minus results in the formation of ionic compound Mg2 positive, O2 negative. In this compound, the electrovalency of magnesium and oxygen is +2 and -2 respectively. General characteristics of ionic solids. The ionic solid has the following characteristic properties. Crystalline nature. In general, ionic compounds are crystalline in nature. X-ray studies of these compounds have shown that they do not exist in the molecular form but consist of ions of oppositely charged charges arranged in some definite geometric pattern. Each ion in the crystal is surrounded by a definite number of oppositely charged ions. The geometric arrangement of ions is different for different ionic substances. The mode of arrangement depends upon size of the ion and also on the respective charge on them. For example, in sodium chloride crystal, each sodium ion is surrounded by 6 chlorine ions. This arrangement is extended throughout the crystalline lattice. Point number 2, high melting and boiling point. In general, ionic compounds have high melting and boiling point and high heat of fusion and vaporization. It is because of the strong electrostatic force of attraction between the oppositely charged ions. Consequently, a large amount of energy is required to overcome interionic attraction, which results in the increased melting and boiling point. The variation in melting point in different ionic compounds are mainly due to charges on the ions and ionic radii. The closer the ions in crystal, the larger will be the electrostatic force of attraction and consequently higher will be the melting point. For example, in the case of sodium halides, the melting point decreases from NaF to Nai. As the size of anions increase from F to Cl-, the force between Na positive and halide ion become weak and consequently melting point decreases as given below. Salt NaF, its melting point in Kelvin 1270. Salt NaCl, its melting point 1073 Kelvin. Salt NaBr, its melting point 1023. Salt NaI, sodium iodide, its melting point 924 Kelvin. In case the interionic distance is almost same between two compounds, the melting point is determined by the charges of the ions. For example, NaCl and BeO have almost similar internuclear distances. For NaCl it's 2.80 angstrom and for BeO it's 2.77 angstrom. The melting point of NaCl is 1073 Kelvin while the melting point of BeO is 2197 Kelvin. The higher melting point of BeO is due to stronger interionic attraction between double charged Be2 positive and O2 minus ion in comparison to attraction between singly charged Na positive and Cl minus ions. Hardness. Ionic compounds are hard and rigid. The hardness of the ionic compound is due to the strong electrostatic force of attraction between oppositely charged ions. Hardness of this compound increases with the decrease in interionic distances and increase in ionic charge for crystals with similar structure. For example, LiCl, lithium chloride and strontium oxide have similar structures and their interionic distances are also the same, that is 2.57 angstrom. Strontium oxide is harder than lithium chloride because of higher charge of ions in strontium oxide than in lithium chloride. Similarly, NaCl and CaS have similar structures and nearly the same interionic distances, but CaS is harder than NaCl because of high charge on ions. The ions in solution acquire greater freedom of motion. Another favorable factor is that water acts as a dipole having negative and positive ends. When an ionic compound is dissolved in water, the positive end of a dipole interacts with the negative ion, while the negative end of the dipole interacts with positive ion. Due to the strong interactions between the ions and the and the solvent, large amount of energy is released. This is known as hydration energy. The hydration energy released is greater than the crystal energy which holds the ion. Consequently, the crystal lattice breaks and goes into the solution. Point number 6, conduction of electricity. The ionic solids consist of ions. They do not conduct electricity in solid state. The reason is that the ions and cations on account of electrostatic forces are held strongly at particular positions in crystal lattice and are not free to move, hence no current flows. However, as the temperature is raised, there is increase in kinetic energy of the ions. When the substances are heated to high temperature so that they melt, the kinetic energy of the ions increases to such a large extent that they overcome the attractive forces and become mobile and are thus able to conduct electricity in the molten state. Ionic reaction. Ionic compounds split up into oppositely charged ions when dissolved in water. The chemical reactions of ionic compound are characteristics of the constituent ions and are known as ionic reactions. Such reactions occur almost instantaneously. Non-directional character. The ionic bond is non-directional. In ionic compounds, each ion is surrounded by oppositely charged ions held together by electrostatic forces. These forces are uniformly distributed all around the ion, that is, electric field is non-directional. Close packing of identical solid spheres. Before discussing the structures of some ionic compounds, it is worthwhile to understand the packing of constituent particles, atoms, ions and molecules in the crystal. In the formation of crystals, these particles get closely packed together. The closely packed arrangement is that in which maximum available space is occupied. The closer the packing, the greater is the stability of the crystal. In order to understand the packing of constituent particles of a crystal, let us consider the packing of Hertz spheres of equal size in 3 dimensions. If a number of spheres of equal size are put in a container and shaken, it is observed that they pack themselves in 2 common ways, such as shown in figure 3. In arrangement 1, the spheres are packed in such a way that the rows have horizontal as well as vertical alignment. In this arrangement, the spheres are found to form squares. In arrangement 2, the spheres are packed in such a way that spheres in every second row are placed in the depressions between the spheres of the first row. In the third row, the spheres have vertical alignment with spheres in first row. A comparison of the 2 arrangements of spheres shows that in arrangement 1, the spheres are less closely packed than in arrangement 2. It has been calculated that in first arrangement only 52.4% of the available space is occupied. The remaining 47.6% of the sphere is empty and is called void volume. In the second arrangement, 60.4% of the space is filled and 39.6% of the space is empty. This arrangement 2 is more economical and it represents a close packing of spheres. It can be seen that in close packing arrangement 2, the center of 3 nearest spheres are at corners of an equilateral triangle. Moreover, each sphere is in contact with 6 other similar spheres shown shaded in figure 4b. The number of nearest neighbors with which a given sphere is in contact is called coordination number. This coordination number of each sphere in the close pack arrangement is 6. Thus, the arrangement 2 represents closest packing of spheres in a layer. We can build other layers above the first layer to extend the packing in the 3 dimensions. Let us label the spheres in the first layer as A. It is clear from figure 5a that there are 2 types of voids hollow in the first layer. They are marked as A and B. All the hollows are equivalent, but the spheres of the second layer may be placed either on hollows which are marked A or on either set of hollows marked B. It may be noted that it is not possible to place spheres on both type of hollows. Thus, while building the second layer, only half the hollows are occupied and half the hollows remain unoccupied. Let us place the spheres on hollows marked B to make the second layer, which may be labeled as B layer. The second layer is indicated by dotted circles. Figure 5. In the first layer, there are 2 types of hollow marked A and B. The second layer is built up by placing the spheres on hollow marked B. The hollows marked A remain unoccupied. When we come to packing of third layer, there are again 2 types of hollows available. One type of hollows marked A are unoccupied hollows of first layer. The other type of hollows are hollows in the second layer marked C. Thus, there are 2 alternatives to build the third layer as discussed below. The spheres of third layer may be placed on the hollows on the second layer, that is marked C. In this arrangement, each sphere of third layer lies directly above those in first layer. In other words, the third layer becomes identical to the first layer labeled A. This arrangement, if continued indefinitely in the same sequence, is represented as AB, 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 dash, dash, dash. This type of packing is known as hexagonal close packing. In figure 6, building of 3 layers by placing spheres on the hollows of second layer marked C result into AB, AB. Packing known as figure A, HCP, by placing spheres on the holes left vacant in first layer resulting into ABC, ABC, packing known as CCP or FCC, which is shown in figure B. In this figure, the spheres of third layer are not shown because they are identical to A layer. For simplicity, it may be drawn as shown in figure 7. The second way to arrange spheres in the third layer is to place them over the hollows marked A, unoccupied hollows of the first layer. This gives rise to a new layer labeled as C. This will give a different type of close packing arrangement. However, it can be shown that the spheres in the fourth layer will correspond with those in the first layer. This type of arrangement may be represented as ABC, ABC, A, dot, dot, dot. It is also known as cubic close packed arrangement and is abbreviated as CCP. It is clear from figure 8 that there is sphere at the center of each face of the cube. Therefore, this arrangement is also known as face-centered cubic arrangement and is abbreviated as FCC. It may be noted that both types of packing are equally economical, though these have different forms. In both these arrangements, 74% of the available volume is occupied by the spheres. In addition to above two closed packed arrangements, there is another arrangement of packing spheres known as body-centered cubic arrangement. It is abbreviated as BCC. In this arrangement, the spheres in the first layer of closed packing are slightly opened up. This is shown in figure 9. The spheres in the second layer, shown by dotted spheres in figure 9, are placed at the top of hollows in the first layer. It is clear from the figure that each sphere in the second layer is in contact with 4 spheres of the first layer. In the third layer, spheres are placed exactly above the first layer. Therefore, in this arrangement, each sphere is in contact with 8 spheres, 4 in the layer below it is and 4 in the layer above it. This arrangement can also be described as cubic arrangement, in which there are 8 spheres at the corners of a cube and 1 sphere is in the central body of a cube. This structure may be drawn as shown in figure 9. In BCC arrangement, only 68% of volume is occupied, and therefore it is less economical than HCP and CCP arrangement. Interstitial sites in closed packing arrangements. We have observed that even in the closed packing of spheres, certain hollows are left vacant. These holes are voids in the crystal are called interstitial sites. The sites are named depending upon the geometry in terms of the position of the atom surrounding the hole. For example, in the closed packing arrangement of sphere, the center of 3 spheres lies at the vertical of an equilateral triangle. The empty spaces between these spheres is called triangular site. There are 2 important types of interstitial site in the crystal. These are tetrahedral site and octahedral site. Tetrahedral site. This type of site is formed when a sphere in the second layer is placed above the 3 spheres touching one another in the first layer. This is shown in figure 10. The centers of the 4 spheres are disposed toward the center of a regular tetrahedron. It may be noted that the shape of the hole is not tetrahedral, but the arrangement around the hole is tetrahedral. Octahedral site. This type of site is formed at the center of 6 spheres, the centers of which form a regular octahedron. This is shown in figure 11. From the figure, it is clear that the octahedral site is formed by 2 sets of equilateral triangles which point in opposite directions. Ionic structures. We have learned that in the formation of crystals, the constituent particles, atoms, ions or molecules get closely packed together. The closely packed arrangement is that in which maximum available space is occupied. The closer the packing, the greater the stability of the crystal. All crystalline substances have definite orderly arrangement of their constituent particles in 3 dimensions. The regular arrangement of the constituent particles of a crystalline solid in 3-dimensional space is called space lattice. If we carefully look at space lattice, it is observed that we can select a smallest repeating pattern or motif which is repeated over and over again in the whole crystal lattice. The smallest repeating unit in space lattice, which when repeated over and over produce the complete lattice, is called unit cell. The smallest repeating pattern or unit cell represents the shape of the entire crystal. It must be remembered that while drawing the structures of ionic solid, we do not draw the complete crystal lattice but a unit cell. In the simple ionic compounds, generally 2 types of arrangement are possible. These are cubic close packing CCP arrangement and hexagonal close packing HCP arrangement. The larger ion, that is anions, adopt these arrangements. These are shown in figure 12 CCP, and in figure 13 there is HCP. The CCP arrangement, also known as FCC arrangement, can be obtained by placing atoms at all the corners of the cube and in the center of each face. There are 6 faces. This arrangement is also called ABC type arrangement. There are 4 atoms per unit in this arrangement. The HCP arrangement, which is shown in figure 13, is drawn by placing atoms at all the corners of the hexagonal face and at their centers. One layer is made in between these 2 identical layers. If we join opposite corners of a face, we get 6 triangles, sides surrounded by 3 atoms. The second layer is formed by placing the atoms above alternative triangles. This arrangement is also called AB type arrangement. The cations occupy the interstitial sites of this arrangement. As already learned that there are 2 types of sites which are commonly occupied. These are octahedral sites and tetrahedral sites. There are 2 tetrahedral sites for each atom and 1 octahedral site for each atom. Let us visualize these sites in this arrangement. Location of interstitial sites in closed packed arrangements. In CCP arrangement, the octahedral sites in CCP arrangement are between the location of interstitial sites in closed packing arrangements. Number 1. CCP arrangement. The octahedral sites in CCP arrangement are between the two anions. Obviously, these are at the center of every edge and in the body center as shown in figure 14. In this figure, only the octahedral sides of top face are shown by dark spheres. The hollow spheres represent anions. If we carefully see the CCP arrangement, we observe that it has 8 small cubes. Each cube has 4 anions at the alternate corners. The center of the small cube becomes the tetrahedral side. There are 8 small cubes and therefore there are 8 tetrahedral sides. In figure 15b, only one tetrahedral side is shown. HCP arrangement. In HCP arrangement, the octahedral and tetrahedral sides are shown in figure 15a and b. We have learned earlier that the second layer in HCP arrangement is made by placing atoms on the alternative triangles in the face. For example, B layer is formed by placing atoms above the triangle marked crossing in figure 15. The octahedral sides correspond to the other triangle not marked by crosses in the figure. The tetrahedral sides are shown above and below each atom. For simplicity, only the tetrahedral sides above the bottom layer are shown filled. Let us discuss some important structure of two types AB and AB2. In the structure of AB type, the two types of anions A positive and B negative have same coordination number, that is number of nearest neighbors. However, in the compound AB2 or A to B types of two types, the two kinds of atom A positive and B negative have different coordination number, which are in the ratio 2:1 or 1:2 respectively. It may be noted that we consider close packed arrangement of ions, though the close packed arrangement may slightly expand in order to accommodate the opposite ions. As a result, the structure may be slightly open up structure, but the close packed structure is often a good starting point for the discussion of these structures. Structure of AB type ionic solids. Three commonly found AB type structure are sodium chloride, rock salt or NaCl structure, zinc blend structure and cesium chloride structure. Now point number one, structure of sodium chloride NaCl. The unit cell of sodium chloride is shown in figure 16. In this structure, the sodium ions are represented by solid circle and chloride ions are by hollow circle. The salient features of this structure are as follow. The chloride ions are arranged in cubic close packing type arrangement. In this arrangement, Cl- ions are present in the corners of the cube and the center of each face. As discussed earlier, this arrangement is also known as face-centered cubic arrangement. The sodium ions Na positive occupy all the tetrahedral octahedral sites. There is only one octahedral site per atom in a closed packed lattice, therefore there will be one Na positive for every Cl ion. This means that ratio of Na positive and Cl negative ion in the structure is 1:1. In other words, the stoichiometry is 1:1 in sodium chloride crystal. This stoichiometry can be understood by counting the number of Na positive and Cl minus ions which contribute to the unit cell as discussed below. Figure 16 shows that there are 8 chlorine ions at the corner and 6 at the face of the unit cell. We can easily understand from the figure that each ion at the corner is shared between 8 unit cells, and its contribution per unit cell is 1/8. Similarly, each ion on a face is shared by 2 unit cells, so that its contribution per unit cell is 1/2. So 8 chlorine ions at the center equals to 8 multiply 1/8, which gives 1 chlorine ion per unit cell. Similarly, 6 chlorine ions at the faces, which equals to 6 into 1/2, which gives 3 chlorine ions per unit cell. Total number of Cl minus ions in the unit cell becomes 1 plus 3, which is equal to 4. There are 12 Na positive ions on the edges and 1 inside the shell. It can be easily seen that each ion on the edge is shared by 4 unit cells and its contribution per unit cell is 1/4, while the ion at the body center contributes only to 1 unit cell. Therefore, 12 Na positive in the edges, which equals to 12 into 1/4, which gives 3 Na positive ions per unit cell. 1 Na positive ion inside the cell, which gives 1 Na positive ion per unit cell. Total number of Na positive ions in the unit cell equals to 3 plus 1, which is equal to 4. Thus, the stoichiometry of Na positive and Cl minus ions becomes 4:4 or 1:1. In this structure, each Na positive ion is surrounded by 6 chlorine ions, which are disposed towards the corners of a regular octahedron. Similarly, each Cl minus ion is surrounded by 6 Na positive ions. Thus, the coordination number of Na positive ion as well as Cl minus ion is 6. This type of arrangement is adopted by most of the alkali metal halides like NH4Cl, NH4Br, NH4I and AgF, AgCl, AgBr, etc. Now we come to the next topic, which is structure of zinc sulfide. It has two types of structure known as zinc blend structure and Woodside structure. So first we discuss zinc blend structure or ZNS. The unit cell of zinc blend structure is shown in figure 17. In this structure, the zinc ions are represented by solid circles and the sulfide ion are represented by hollow circle. The salient features of this structure are as follow. The sulfide ions S2- are in cubic close packing CCP type arrangement. In this arrangement, the S2- ions are present at corners of the cube and at the center of each face. The zinc ions Zn2 positive occupy half of the tetrahedral site. There are two tetrahedral sites per atom in a closed packed lattice. This means that there are two tetrahedral sites available for every S2- ion. In this arrangement, only half of the tetrahedral sites are occupied by Zn2 positive ions. Therefore, there is only one Zn2 positive for every S2- ion. So, the stoichiometry of the compound is 1:1. In this structure, each zinc ion is surrounded by 4 sulfide ions which are disposed toward the corner of a regular tetrahedron. Similarly, each S2- ion is surrounded by 4 Zn2 positive ions which are also disposed toward the corner of a regular tetrahedron. The arrangement around one Zn2 positive ion and one S2- ion is also shown in figure 17. Thus, the cations and anions are present in equivalent position and the coordination number in zinc blend is described as 4:4. This structure is also adopted by compounds such as ZNO, CuCl, CuBr, CuI, BeS and etc. Now we come to the next structure, which is Woodside structure. The unit cell for Woodside structure is shown in figure 18. In this structure, Zn2 positive ion represented by solid circle and S2- ions are represented by hollow circles. The salient features of the structure are as follows. The sulfide ions are arranged in hexagonal close packing or HCP arrangement. The zinc ions occupy half of the tetrahedral site. In HCP arrangement, for each S2- ion there are two tetrahedral sites, one above and one below it. In the figure, only tetrahedral sites above the S2- ion are shown filled. The tetrahedral sites below the S2- ion remain vacant. Figure 18 representation of Woodside structure. S2- ion in hollow circle adopt HCP arrangement and Z2- ion in solid circle occupy half the tetrahedral site. There are two tetrahedral sites per atom in the closed packed lattice. This means that there are two tetrahedral sites available for every S2- ion. Since only half of these are occupied by Zn2 positive ions, the stoichiometry of the compound is 1:1. In this structure, each S2- ion is surrounded by 4 Zn2 positive ions which are disposed towards the corner of a regular tetrahedron. Similarly, each Zn2 positive ion is surrounded by 4 S2- ions which are also disposed towards the corner of a regular tetrahedron. The arrangement around one Zn2 positive ion and one S2- ion is shown in figure 18. Therefore, the coordination number of Zn2 positive and S2- ions in the Woodside structure is 4:4. Other example of this type of structure are ZNO and CDS, CAS, CBEO, etc. Basic difference between zinc blend and Woodside structure. It will be noted that the basic difference between zinc blend and Woodside structure is that in zinc blend structure, the sulfide ions are arranged in CCP type of pact, whereas in Woodside structure, they are arranged in HCP type of arrangement. The coordination number of Zn2 positive and S2- ion are 4:4 in both the cases. Now we come to the next topic, which is structure of cesium chloride CaCl. The unit cell of CaCl is shown in figure 19. In this structure, cesium ions are represented by solid circles, whereas chloride ions are represented by hollow circles. The salient feature of CaCl structure are as follows. The Cl- ions are arranged in the simple cubic arrangement. In this arrangement, the Cl- ions are present at all the corners of the cube. The cesium ions occupy the cubic sides. There is Cs positive ions are present at the body center of the cube. It is clear from figure 19a that there are 8 Cl- ions at the corners of the cube. Each ion at the corner is shared between 8 unit cells. and its contribution per unit cell is 1 upon 8. Therefore 8 Cl minus ion are at the corner, which gives 8 multiply 1 upon 8, 1 chlorine ion per unit cell. There is also one Cs positive ion in the body center and its contribution per unit cell is 1. Thus for Cs positive ion there is one Cl minus ion, so that its stoichiometry is 1:1. In this structure, each Cs minus ion is surrounded by 8 Cl minus ions, which are disposed towards the corners of a cube. This is clear from figure 19a. When the unit cell is extended as shown in figure 19b, it becomes clear that each Cl minus ion is also surrounded by 8 Cs positive ions. Thus both types of ions are in equivalent position, therefore the coordination number of Cs positive and Cl minus ion are 8:8. CaCl type of arrangement is adopted by CsBr, cesium bromide, cesium iodide, TiCl, TiBr and etc. Note, it may be noted that structure is sometimes wrongly described as body-centered cubic, but this is a misnomer because the body-centered cubic structure is one, which are the same atoms at the body center as well as the corners. But in CaCl, the atoms at the corners are different than the atom in the center. Now we come forward to the next topic, which is structure of Ab2 type ionic solids. Fluoride structure of CaF2. The unit cell of CaF2 is shown in figure 20. The calcium ions are represented by solid circles and fluoride ions are represented by hollow circles. The CaF2 structure may be described as follows. The Ca2 positive ions are arranged in CCP arrangement. In this arrangement, Ca2 positive ions are present at all the corners and at the center of each face of the cube. The fluoride ions occupy all the tetrahedral sides. There are 2 tetrahedral sides per atom in a closed packed lattice. This means that there are 2 tetrahedral sides for every Ca2 positive ion. Since F minus ions occupy all the tetrahedral sides, there will be 2 F minus ion for each Ca2 positive ion. Thus the stoichiometry of the compound is 1:2. In this structure, each F minus ion is surrounded by 4 Ca2 positive ions, which are disposed towards the regular tetrahedron. On the other hand, each Ca2 positive ion is surrounded by 8 F minus ion, which are disposed towards the corners of a cube. Thus the coordination number of Ca2 positive and F minus ion are 8:4. The structure is adopted by large number of fluorides such as CuF2, BaF2, SrF2, PbF2, HgF2, etc. The summary of the structure of ionic solid is given in table 1. So the table 1. Compound NaCl description. AB type. CCP arrangement of Cl minus ion and Na positive in all the octahedral sides. Coordination number for Na positive 6, for Cl minus it is 6. Other example: lithium, sodium, potassium halides, silver chloride, silver bromide, magnesium oxide, etc. ZnS, zinc blend. Description: CCP arrangement of S2 minus ion, Zn2 positive ion in alternative tetrahedral sides. Coordination number: Zn2 positive 4, S2 minus 4. Other example: BeS, CuCl, CuBr, Cui. ZnS, Woodside structure. HCP arrangement of S2 minus and Zn2 positive occupy alternative tetrahedral sides. Coordination number same for Zn2 positive 4, S2 minus 4. Other example: zinc oxide, CdS, CuO. CaCl, cesium chloride. Simple cubic arrangement of Cl minus ion and Cs positive ion in cubic site. Coordination number: Cs positive 8, Cl minus 8. Other example: CsBr, Csi. Now we come to next, that is Ab2 type arrangement. CaF2. CCP arrangement of Ca2 positive and F minus occupy all tetrahedral sides. Coordination number for Ca2 positive it is 8, for F minus ion it is 4. Other example include SrF2, BaF2, CeF2 and etc. Now we have a practice problem. Question number 5. Which of the following statements are false? In zinc blend structure, Zn2 positive ion occupy tetrahedral sites in CCP arrangement of S2 minus ion. And the next question is, sodium chloride has CCP arrangement of Cl minus ion and octahedral sites are occupied by Na positive ion. The next question is, CaCl has body centered cubic arrangement of Cl minus ion. In Woodside structure, S2 minus ion have HCP arrangement and Zn2 positive ions occupy half of the tetrahedral site. So the correct answer are option number 1 is false, option number C is false, and option number A, which states the basic difference between Woodside and zinc blende structure is that zinc sulfide has HCP arrangement while Woodside has CCP arrangement of S2 minus ion. This is also false. So we come to the next discussion, which is termed as radius ratio effect and coordination number. Radius ratio is an important parameter to predict the coordination number from the relative sizes of the ions in ionic structures. Ionic solids are made up of cations and anions which have definite arrangements. Each ion is surrounded by a number of ions of opposite charges. For example, in an ionic crystal of the type A positive, B negative, A positive ions are surrounded by a definite number of B minus ions. This number is called coordination number of A positive. Similarly, the number of A positive ions which are surrounding a B negative ion is called coordination number of B minus ion. The arrangement of ions in crystal, geometric shape, and the coordination number of ions depend on the relative sizes of the ions or ratio of the radii of the ions. The ratio of the radii of positive and negative ions is called radius ratio. Thus, radius ratio equals to radius of positive ion R positive by radius of negative ion R negative. Radius ratio plays a very important role in determining the structure of ionic solid as discussed below. We know that the cations and anions in the ionic compound are held together by strong electrostatic forces. As a result, the ions try to arrange themselves in a geometric arrangement in which the attraction between the opposite charges are maximum and the repulsion between the similar charges are minimum. Consider, for example, an ionic crystal in which a cation A positive, shown in dark circle, is surrounded by octahedrally by 6 anions B positive, which are shown in hollow circle. In figure 22, only 4 B minus ions are shown for simplicity. There will be 2 more B minus ion, one above and the other below the A positive ion, but this I have omitted for the sake of clarity. The most stable arrangement is one in which the anions are touching each other and the cations simultaneously, as shown in figure 22a. In this case, the attraction will be maximum and the repulsion will be minimum. Such a structure will be quite stable. However, if the size of anions is less, cations same, the anion will no longer touch other anions and the structure will be unstable, as shown in figure 22b. Similarly, if the size of anion is large, cations same, all the ions will not be able to touch the cation simultaneously. The structure will also be unstable, as shown in figure 22c. Let us understand as how the change in radius ratio R positive upon R negative changes the structure of the compound. Consider the stable structure in which all the anions are touching each other and the cations simultaneously, octahedral arrangement, but only 4 are shown for clarity. Now if we decrease the radius ratio, either by decreasing the size of cation or by increasing the size of anion, then the structure will become unstable. All the anions will not be able to touch simultaneously the cation. In order to touch the cation, the anions have to go closer and closer, and therefore repulsion will increase. When the radius ratio is further decreased, the stage will reach when one or more anions may be pushed away, so the remaining anions fit around the cation, giving more stable structure. In other words, there may be change in coordination number from 6 to 4. Alternatively, if we increase the radius ratio either by increasing the size of cation or by decreasing the size of anion, the structure will become unstable. All the anions will no longer be touching one another. If the radius ratio is further increased, the anions will be going farther and farther apart. Consequently, stage may reach when more number of anions may be able to fit around the cation, giving more stable structure. In other words, there may be change in coordination number from 6 to 8. This means that there is upper and lower limiting radius ratio for which the coordination number 6 is stable. It has been calculated that octahedral coordination number 6 is stable for the radius ratio in the range of 0.414 to 0.732. That is, if the radius ratio is in this range, only then the cation will be able to keep 6 anions in contact with it. If the radius ratio is less than 0.414, the coordination number will decrease to 4, and if radius ratio is more than 0.732, the coordination number will increase. Similarly, for the radius ratio ranging between 0.225 to 0.414, the tetrahedral site will be preferred. in which coordination number of cation is 4. For the radius ratio ranging between 0.155 to 0.225, trigonal site will be preferred in which coordination number of cation is 3. On the higher side of octahedral site, if radius ratio is above 0.732 cubic side, coordination number 8 will be formed. Thus, we find that radius ratio is a very important factor in determining the most stable type of arrangement of ions in the crystal lattice of an ionic solid. The permitted coordination number and structural arrangement of anions around cation are given in table 2. Limiting radius ratio 0.155 to 0.225, permitted coordination number is 3. Structural arrangement plain triangular, example boron oxide. Limiting radius ratio 0.225 to 0.414, permitted coordination number 4. Structural arrangement tetrahedral, example zinc sulfide. Limiting radius ratio 0.414 to 0.732, permitted coordination number is 6. Structural arrangement octahedral, example NaCl. Limiting radius ratio 0.732 to 1.000, permitted coordination number 8. Structural arrangement cubic, example CaCl. The application of radius ratio rule may be illustrated by the following example. The radius of Na positive ion is 0.95 angstrom and that of Cl minus ion is 1.81 angstrom. Hence the radius ratio is R positive to R negative, that is radius of Na positive to radius of Cl negative, 0.95 to 1.81, which gives 0.5 to 4 angstrom. This ratio lies between 414 and 0.732. Hence, Na positive ion prefer to occupy octahedral site, having coordination number 6 in the close packed lattice of Cl minus ion. The radius ratio of Rb positive and I minus ion are 1.47 angstrom and 2.16 angstrom respectively. Hence, the radius ratio will be 0.68 angstrom. The radius ratio lies between 0.414 to 0.732 and therefore Rb positive prefer to occupy octahedral holes having coordination number 6. Limitation of radius ratio rule. Although radius ratio rule is a useful concept for predicting and understanding the structure of ionic compound, yet it is not perfect. It has many limitations also. Some of the common limitations of radius ratio are: the radius ratio rule applies only to the packing of Herd spheres of known size. This is far from reality. Anions are not Herd but are polarizable under the influence of cations. The extent of polarization of the anions leads to covalence and results in serious errors in the application of radius ratio rule. For example, the radius ratio Rag positive to Ri minus for AgCl is 0.52. This indicates coordination number 6 NaCl structure, but actually silver iodide is 4 coordinated tetrahedral lattice with zinc blend structure. Many serious errors occur for the coordination number 6 versus 8. Coordination number 8 is found only in CaCl, CsBr and CsI. Although radius ratio calculation predicts CaCl as coordination number 8, structure for oxide of larger divalent metal ions such as Ba2 positive, Sr2 positive and Pb2 positive, yet no 8 coordination oxide MO had been observed. Radius ratio rule fails to explain why some compound crystallize in more than one modification having different coordination number. For example, thallium chloride crystallizes in 2 forms adopting NaCl structure having coordination number 6 and CaCl structure having coordination number 8. Effective radius of a cation is greatly influenced by the anion, so that radius ratio changes. For example, silver fluoride and sodium fluoride crystallize out in NaCl type structure with coordination number 6. Now if we assume that size of F minus ion remains constant, then Ag positive is bigger than Na positive. On the other hand, for a given size of Cl minus ion in AgCl, NaCl, the size of cations are reversed, that is Na positive is bigger than Ag positive ion. Internuclear distance M minus X in angstrom. It is also true for their bromides. This is understandable because Ag positive ion is softer than Na positive and introduce relatively more covalent character with polarizable anions like Cl minus and Br minus ions. These changes in size of cations may introduce errors in the radius ratio rule calculations and predictions. Thus, radius ratio rule calculations are very useful for predicting coordination number of ionic or partially ionic compounds, but such predictions can be misleading when atomic and ionic radii are not well defined. Now we come to the next topic, that is calculation of radius ratio. We have learned that stable ionic lattices have commonly 4 types of interstitial sites, namely trigonal, tetrahedral, octahedral and cubic, corresponding to coordination number 3, 4, 6 and 8 respectively. In general, the size of trigonal site is smaller than size of tetrahedral site, which in turn is smaller than size of octahedral site. The size of octahedral site is smaller than that of cubic site. The size of site varies with the size of spheres surrounding it. The radius of a small sphere, cation, which can perfectly occupy a given site created by large spheres, can be calculated by simple geometry. These are generally calculated in terms of ratio of the radius of cation to that of anion as given below. Radius ratio for triangular site. A triangular site is formed when 3 spheres lie at the vertices of an equilateral triangle as shown in figure 25. Let R positive and R negative be radii of cation and anion respectively in an equilateral triangle DBC. BC equals to CD equals to BD equals to 2R. If A is center of triangle and hence of the cation, then BE equals to R minus and AB equals to R positive and R negative. Since delta ABA is right angle triangle, hence cos angle ABE equals to BE upon AB. That is cos 30 degree equals to R minus upon R minus plus R positive. We know cos 30 degree equals to root 3 by 2. So root 3 by 2 equals to R minus upon R minus plus R positive. On inverting both sides, 2 upon root 3 equals to R minus plus R positive upon R minus. On simplifying the given equation, we get 2 upon root 3 equals to 1 plus R plus upon R minus. Taking 1 on the next right hand side, we get R positive upon R negative equals to 2 upon root 3 minus 1, 2 minus 1.732 upon 1.732, which gives 0.155. Thus the limiting R positive to R negative ratio for triangular site is 0.155. Thus for cations to occupy trigonal side of the anion, the radius ratio should not be smaller than 0.155 angstrom. Only B3 positive ions can fit in such small site in its oxide B2O3. Radius ratio for tetrahedral site. A tetrahedral site in a cube is shown by placing spheres at the alternate corners as shown in figure 26. A stable tetrahedral arrangement has 4 anions at the corners touching each other and also the cation placed at the center. However, for simplicity, the cations and anions are shown by distant circles. Actually, the cations and anions are touching one another. Suppose the anions are present at the alternate corners of a cube and the cation occupies a tetrahedral side. Suppose A is the length of each side and R positive and R negative are radii of cation and anion respectively. In figure, AC is phase diagonal in delta ABC. AC square equal to AB square plus BC square, or AC equal to under root AB square plus BC square, which implies under root A square plus A square equals to 2A square. A square is removed from the root, which gives us under root 2A. The two anions at the phase diagonal, though shown by distant circles, are actually touching each other. So AC equal to R minus plus R minus, which equals to 2R minus. So 2R minus equals to under root A, R minus equal to under root 2A by 2, which gives A upon under root 2. AD is the body diagonal in delta ADC. AD square equal to AC square plus CD square. So AD equals to under root AC square plus CD square. AC was 2A square, so 2A square plus A square, which gives us under root 3A. Or the cation is present at the center of body diagonal AD, so that half the length of the diagonal is equal to sum of the radii of the cation and anion. Thus R minus plus R plus equal to AD by 2, which is equal to under root 3A by 2. Dividing equation 3 by equation 1, equation 1 is R minus equal to A upon root 2, and equation 3 is R minus plus R positive equal to AD by root 2, which equals to under root 3A by 2. So we get radius ratio for tetrahedral site is 0.225 angstrom. Radius ratio for octahedral site. An octahedral site is shown in figure 27. A cross section through an octahedral site shows that the 4 anions are at the corners of square and the cations is at the center. 1 anion each at the top and bottom of the plane formed by the 4 anions also touch the cation ABCD square. Suppose each side of the square is A and R positive and R negative are the radii of cation and anion respectively. In right angle ABC, AC square plus AB square equal to BC square. AC square equal to AB square plus BC square, or AC equal to under root AB square plus BC square, which gives under root 2A. But it is evident from figure that AC equal to R minus plus 2R positive plus R negative, which gives 2R minus plus 2R positive. To R minus plus 2R positive equal to under root A. R minus plus R positive equal to under root 2A by 2. It is clear from the figure that AB equals to A equal to 2R minus, so R minus equal to A by 2. Dividing equation 1 by equation 2, we get radius ratio for tetrahedral side is as 0.414. Now radius ratio for cubic side. A cubic side is shown in figure 28. The spheres are not shown touching one another for the sake of simplicity. Suppose the length of each side of the cube is A and R minus and R plus and R minus are the radii of cation and anion respectively. In figure AB equal to 2R minus equal to A or R minus equal to A by 2. AC is phase diagonal in delta ABC. AC square equal to AB square plus BC square, or AC equal to under root AB square plus BC square, which gives under root 2A. AD is both diagonal in delta ACD. AD square equal to AC square plus CD square, or AD equal to under root AC square plus CD square, which gives under root 3A. As evident from the figure, body diagonal AD equal to R minus plus 2R plus R minus, which gives 2R minus plus 2R positive. Therefore 2R minus plus 2R positive equal to under root 3A, or R minus plus R positive equal to under root 3A by 2. Dividing this equation, we get radius ratio for tetrahedral for cubic side as 0.732 angstrom. Lattice defects. That comes the next topic. Ionic crystals have well-defined order of the constituent ions. An ionic crystal which has the same unit cell containing the same lattice point throughout the whole of crystal is known as ideal crystal. However, such ideal crystal exists only at absolute zero Kelvin temperature. At any temperature above 0 Kelvin, the crystal have some departure from complete ordered arrangement. Any deviation from completely ordered arrangement in a crystal lattice constitutes a disorder or a defect. The crystal may have additional defect due to presence of some impurities. The term disorder or imperfection is generally used to denote departure from perfectly ordered state of the constituent of the crystal. These imperfections will not only change the properties of the crystal but also give rise to new properties. There are commonly two types defect in crystal. Defect in stoichiometric crystal, defect in non-stoichiometric crystals. A. Defect in stoichiometric crystals. Stoichiometric compounds are those in which number of positive and negative ions are exactly in the ratios indicated by their chemical formulae. For simplicity, we can consider the compound of the type AB having equal number of A positive and B negative ions. The defects in these types of compound are called stoichiometric defects. In these compounds, two types of defects are generally observed. These are Schottky defect and Frenkel defect. So we discuss first Schottky defect. This defect was discovered by German scientist Schottky in 1938. Arises if some of the atoms or ions are missing from the normal lattice site. The lattice site which are unoccupied are called lattice or vacancies or holes. Since the crystal is to remain electrically neutral, equal number of cations and anions are missing. The ideal AB crystal is shown in figure 29. The existence of two holes, one due to missing cation and other due to missing anion, are shown in figure 30. Conditions causing Schottky defect. This type of defect is usually observed in strongly ionic compound having high coordination number and ions, cation and anion of almost similar size. For example, NaCl, KCl, KBr and CaCl ionic solid have Schottky defect. It has been observed that in NaCl there are about 10 to the power 6 Schottky pairs per centimeter cube at room temperature. In 1 centimeter cube there are about 10 to the power 22 ions, and this means that there will be one Schottky defect per 10 to the power 6 ions in NaCl. Because of the presence of large number of vacancies in crystals, its density is markedly lowered. Now next comes Frenkel defect. This defect was discovered by Russian scientist Frenkel in 1926. It arises when an ion is missing from its normal position and occupies an interstitial site between the lattice points. The existence of one hole due to missing cation from its normal position occupying an interstitial position is shown in figure 31. In this case also the crystal remains electrically neutral because the number of anions and cations remain the same. Conditions causing Frankel defect. This defect generally occurs in compound in which coordination number is low, anions are much larger in size than the cation. In pure alkali metal halides, this defect are not very common because the ions cannot get into interstitial positions due to the large sizes. These defects can be found in silver halides such as AgCl, AgBr, AgI, etc. Because of the small size of the Ag positive ion, it can go into the interstitial side. We observe that vacancies or holes are present in crystal with Schottky as well as Frankel defect, but the former leads to decrease in the overall density of the substance, but the latter does not. In certain ionic solids such as AgBr, both Schottky and Frankel defects occur. Consequences of Schottky and Frankel defect. Schottky and Frankel defect in crystal lead to some interesting consequences. These are given below. Because of the presence of this defect, the electrical conductivity of crystal increases. When an electric field is applied, a nearby ion moves from its lattice side to occupy a hole. This results in creating a new hole and another nearby ion moves into it, and so on. This process continues and a hole thereby moves from one end to the another end. Thus it conducts electricity across the whole of the crystal. Due to the presence of holes in the crystal, its density decreases. However, it may be noted that density decreases only for crystals having Schottky defect. The presence of holes also decreases the lattice energy or the stability of the crystal. The presence of too many holes may cause a partial collapse of the lattice. The closeness of similar charges in Frankel defect tends to increase the dielectric constant of the crystal. Differences between Schottky and Frankel defect. Schottky defect, it is produced because of missing atoms or ions from the normal side. It is produced when some atoms or ions are displaced from the normal side and occupy interstitial side. The presence of Schottky defect lowers the density of the crystal, whereas the Frankel defect does not affect the density of the crystal. It is generally shown by ionic solid having high coordination number and in which cations and anions are of equal sizes. Example, NaCl, CsCl. It is generally exhibited by ionic solid having low coordination number and in which anions are larger in size than cations. Example, AgCl, ZnS. Now next comes defect in stoichiometric crystals. The compounds in which ratio of positive and negative ion present in the compound differ from that required by ideal chemical formula of the compound are called non-stoichiometric compounds. The defects in this compound are called non-stoichiometric defects. Vanadium oxide, for example, has a formula VOX, where X lies between 0.6 and 1.3. Similarly, iron 2 oxide samples contain more oxygen atoms than iron atoms, while samples of zinc oxide ZnO usually has excess of zinc atoms than oxygen atoms. However, it may be noted that in each case, the electrical neutrality of the crystal is maintained. These are of two types depending upon whether positive ions are in excess or negative ions are in excess. These are also known as metal excess defect and metal deficiency defect, respectively. Some of these examples are given below. A. Metal excess defect. In this defect, the positive ions are in excess. This may arise due to following two ways. Anion vacancies. In this case, negative ions may be missing from the lattice side, leaving a hole in which the electrons remain entrapped to maintain the electrical neutrality. This is shown in figure 32. Evidently, there is an excess of positive or metal ions, although the crystal as a whole is electrically neutral. This type of defect is observed in those crystals which are likely to form Schottky defect. For example, in alkali metal halides, anion vacancies are produced when alkali metal halide crystals are heated in the atmosphere of the alkali metal vapors. The metal atoms get deposited on the surface of the alkali metal halide crystals. Halide ions move into the surface and combine with metal atoms. The electrons thus produced by the ionization of the metal atom diffuse into the crystal and get trapped at the ion vacancies. The electrons trapped in ion vacancies are referred to as F centers. This gives very interesting properties. For example, the excess of potassium in KCl makes the crystal appear violet. Excess of lithium in LiCl makes the crystal appear pink. Excess cation occupying interstitial side. In this case, there are extra positive ions occupying interstitial sides and the electron in another interstitial side to maintain electrical neutrality. This is shown in figure 33. These defects may be visualized as the loss of non-metals atom which leave their electrons behind. The excess metal ions occupy interstitial position. This type of defects is found in crystals which are likely to develop Frankel defect. The common example is zinc oxide. Zinc oxide loses oxygen reversibly at high temperatures and turns yellow in color. The excess Zn2 positive ions are trapped in interstitial sites and equal number of electrons are trapped in the neighborhood to balance the electrical charge. These electrons give rise to enhanced electrical conductivity. Consequences of metal excess defects. The crystals with metal excess defect conduct electricity due to the presence of free electrons. However, the conductivity is very low because of the number of defects and therefore the number of free electrons is very small. Because of low conductivity as compared to conductivity of metals, these are called semiconductors. These compounds are also called n-type semiconductors since the current is carried by the electron in the normal way. The crystals with metal excess defect are generally colored. For example, non-stoichiometric sodium chloride is yellow, non-stoichiometric potassium chloride is violet. Next comes metal deficient defects. This contain less number of positive ions than the negative ions. This arises due to two types. Cation vacancies. In some cases, the positive ions may be missing from the lattice site. The extra negative charge may be balanced by some nearby metal ion acquiring ion positive charges instead of one. This is shown in figure 31. This type of defect is possible in metal which show variable oxidation state. The common examples of compound having this defect are ferrous oxide, ferrous sulfide, nickel oxide, etc. In case of iron pyrites FeS, for example, 2 out of 3 ferrous ions in lattice may be converted into Fe3 positive state and the third Fe2 positive ion may be missing from its lattice side. Therefore, the crystal contains Fe2 positive and Fe3 positive ions. This gives rise to exchange of electrons from one Fe2 positive to ion to Fe3 positive ion, in which Fe2 positive changes to Fe3 positive and Fe3 positive changes to Fe2 positive ion. As a result, the crystal has metallic luster. Because of the natural color of iron pyrites and metallic luster, some samples of mineral shine like gold and have been nicknamed as fool's gold. Moreover, since there is exchange of electrons, the substance becomes conductors. Excess ion occupying interstitial sites. In this case, the extra ions may be occupying interstitial positions. The extra negative charge is balanced by the extra charge on the adjacent metal ion. This is shown in figure 35. Such type of defect is not common because the negative ions are usually very large and they cannot easily fit into the interstitial site. Consequences of metal deficient defects. Crystals with metal deficient defects are semiconductor. The conductivity is due to the movement of electrons from one ion to another. For example, when an electron moves from ion A positive, it changes to A2 positive. It is also called movement of positive hole and the substance are called p-type conductors. The conductivity of semiconductor is mainly due to presence of impurities and defect. The semiconductors are very important solid state materials having many important applications in electronics. Semiconductors are important class of compounds which have higher conductivity than insulators and have much lower conductivity than conductors. These are discussed in detail in unit 5. Lattice energy of ionic crystals. The stability of ionic crystals is determined in terms of the lattice energy. Lattice energy is defined as amount of energy released when 1 mole of ionic crystal is formed from its constituent ions in the gaseous state. The formation of 1 mole of the ionic solid from its constituent gaseous ion may be represented as M positive, which is metal in gaseous state, plus X negative in gaseous state, which gives Mx in solid state. Delta H equal to lattice energy or minus U. The lattice energy is expressed by U. The negative sign is used because energy is released in the process. Since ionic bond is formed as a consequence of electrostatic attraction between the oppositely charged ions, there is considerable decrease of potential energy of the system. As a result, if 1 mole of solid ionic compound is broken into its constituent gaseous ions, energy will be needed, which will be numerically equal to the lattice energy. This Mx solid is which gives M positive metal in gaseous state plus X minus in gaseous state. Delta H equal to positive U. In this case, U has positive sign because energy is absorbed in the process. It is obvious that if the compound is stable, a large amount of energy will be needed. This means that higher the lattice energy of an ionic compound, greater will be its stability. Lattice energies of some ionic compound are given in table 3. Lithium fluoride, lattice energy minus 1033. These are all expressed in kilojoule mole inverse. cesium fluoride minus 748, sodium chloride minus 778, sodium bromide minus 752, lithium iodide minus 140, silver chloride minus 895, silver iodide minus 795, and so on. It is evident from the above table that the lattice energy of ionic solid are quite high. This is because of the strong electrostatic attraction between oppositely charged ions present in the solid. Since Coulombic forces of attraction vary directly as the product of the charges, it follows that the higher the valency of the ions, the greater would be the lattice energy of the ionic solid. This lattice energy increases as we move from univalent ionic solid to uni-bivalent ionic solid and then to bi-bivalent ionic solid. Now we discuss the next topic, which is Born-Haber cycle for lattice energies. Born and Haber in 1919 proposed a method to relate the lattice energy of an ionic crystal to other thermodynamic data. This is known as Born-Haber cycle. We have learned that the formation of bond takes place only if there is decrease of energy. As an example, let us consider the energy changes during the formation of sodium chloride from metallic sodium and chloride gas and the formulation of Born-Haber cycle. Na sodium in solid state plus half Cl2 gives us NaCl in solid state. The overall process is thought to take place in the following step: conversion of metallic sodium into gaseous sodium atom. The sodium atom can lose its electron only in the gaseous state and has to be sublimated. The energy required for the conversion of 1 mole of metallic sodium into gaseous sodium is called sublimation energy. It is represented by S. Next topic is dissociation. Next point is dissociation of chlorine molecule into chlorine atoms. Each chlorine molecule consists of 2 atoms of chlorine. The amount of energy required for the conversion of gaseous chlorine molecule into atoms is known as dissociation energy. It is represented by D. Thus the energy required for producing 1 mole of gaseous chlorine atom is D by 2. Conversion of gaseous sodium atom into sodium ions. The amount of energy required to convert 1 mole of gaseous sodium atom into sodium ion in gaseous state is called ionization energy. It is denoted by IE. Conversion of gaseous chlorine atom into gaseous chloride ions. The amount of energy released during the conversion of 1 mole of gaseous chlorine atom into chloride ion is known as electron affinity. It is denoted by EA. Combination of oppositely charged ions to form solid crystal. The oppositely charged Na positive and Cl minus ion attract each other to form solid NaCl crystal. This leads to the release of energy. The amount of energy released when 1 mole of solid crystalline compound is obtained from gaseous ion of opposite charge is called lattice energy. It is denoted by U0. U0 in lower side at the lag side. The overall energy change may be represented as NaS plus half Cl2 gas equal to NaClS. The heat change for this reaction is called heat of formation and it may be denoted as delta H. The various steps may be represented in the form of Born-Haber cycle as shown in figure 35. According to Hess law, the heat of formation of 1 mole of sodium chloride should be the same irrespective of the fact that whether it takes place directly in one step or through a number of steps as shown above. Thus, lattice energy can be calculated knowing the values of different quantities. While using the above relation for lattice energy, a special care should be taken for the signs of various quantities. Positive sign is used for energy absorbed and negative sign is used for energy released. Now we have some example. Calculate the lattice energy of NaCl crystal from the following data by the use of Born-Haber cycle. Sublimation energy of sodium S 108.7 kJ per mole. Dissociation energy of Cl2 D 225.9 kJ per mole. Ionization energy of sodium IE 489.5 kJ per mole. Electron affinity of fluorine EA minus 351.4 kJ per mole. Heat of formation of NaCl delta H minus 414.2 kJ per mole. According to Born-Haber cycle for NaCl, delta U equal to delta H minus S minus 1 by 2 D minus IE minus EA. With delta A, substituting this value, we get lattice energy of NaCl crystal as minus 773.95 kJ mole inverse. Now we have next topic is application of Born-Haber cycle. The Born-Haber cycle has been used for the calculation of many properties. Some of the important are given below. Calculation of heat of formation. Heat of formation of unknown compound can be easily calculated by making a Born-Haber cycle. For example, for NaCl type crystal, heat of formation is given as delta H F equal to S plus half D plus IE plus EA plus U naught. Similarly, for crystal like MgF2, delta HF is given as S plus D plus IE plus 2EA plus U naught. The heat of formation tells us about the stability of the compound. If the heat of formation comes out to be negative, that is the reaction is exothermic, the compound formed will be stable. On the other hand, if heat of formation comes out to be positive, that is the reaction is endothermic, the formation of a compound will be highly unfavorable energetically. From heat of formation, it can be explained why NaCl2 is not formed, though it is expected to have higher lattice energy than NaCl. The heat of formation for NaCl2 by using Born-Haber cycle comes out to be highly positive. Calculation of electron affinity. The Born-Haber cycle can be used for the calculation of electron affinities of some elements which are otherwise very difficult to measure. Heat of formation of a compound may be represented as delta HF equal to S plus half D plus IE plus EA plus U naught. It may be rearranged as EA equal to delta HF minus S minus D minus IE minus U naught. In this case, S, delta HF, D and IE are experimentally determined and lattice energy U naught may be calculated by using Born-Haber cycle. Using the above equation, electron affinity may be calculated. Estimation of proton affinities. The Born-Haber cycle can also be used to calculate the proton affinities of different bases. The proton affinity of special X of species X is defined as the energy released in the reaction Xg plus H positive G equal to X positive G. NH3 in gaseous state plus H positive equal to NH4 positive, delta is equal to Pa, which is proton affinity. This can be easily calculated by considering Born-Haber cycle. According to Born-Haber cycle, delta H is equal to D plus IE plus EA plus Pa plus U naught. Knowing the value of delta HF, D, IE, EA and U naught, we can easily calculate proton affinity. Now we have some examples. Calculate heat of formation of KCl from the following data. Sublimation energy of potassium 102.5 kilojoule per mole. All these energies are in kilojoule per mole. Ionization energy of potassium IE 450.6. Enthalpy of dissociation of chlorine 230.5. Electron affinity of chlorine minus 348.7. Lattice energy of KCl minus 721. Solution. The formation of KCl may be represented by the following Born-Haber cycle. According to Born-Haber cycle, delta HF equal to S plus half D plus IE plus EA plus U naught. Substituting all the values which are already mentioned in the question, we get the value heat of formation of KCl as minus 401.55 kilojoule. Now next question is calculate the heat of formation of magnesium fluoride MgF2 from the following data. Sublimation energy of magnesium 146.4 kilojoule mole inverse. All these values are in kilojoule mole inverse, so I may not be repeating this again. All the values of energies which are described in this questions are in kilojoule mole inverse. Dissociation energy 158.8, ionization energy 2186, electron affinity of fluorine minus 332, lattice energy of MgF2 minus 2922.5. Solution. The formation of MgF2 may be represented by the following Born-Haber cycle. According to Born-Haber cycle, delta HF equal to S plus D plus IE plus 2EA plus U naught. So the heat of formation of magnesium fluoride MgF2 comes out as minus 1096.5 kilojoule. The thermochemical data. The thermochemical data for the formation of argon chloride RgCl is given as heat of dissociation of chlorine minus 243.0, electron affinity of chlorine minus 348.3, ionization energy of argon 1526, lattice energy of argon minus 703.0. Predict whether the formation of argon chloride is favorable or unfavorable. Solution. The formation of argon chloride may be represented by the following Born-Haber cycle. From argon gaseous, ionization energy it converts into argon positive, half Cl2 with the help of dissociation energy d by 2 it converts into chlorine gas, and with of electron affinity it converts into Cl minus. From delta HF AR in gaseous state plus half chlorine 2 in gaseous state combine and form argon chloride. The heat of formation delta HF may be represented as delta H equal to IE plus d by 2 plus EA plus U naught. where I equal to where all these values are given. Substituting these values, we get delta HF as 596.5. Thus the formation of hypothetical argon chloride is endothermic and therefore it is unfavorable. Now we have next topic, which is importance of lattice energy. Stability of ionic compounds. Larger the lattice energy, greater is the stability of the ionic solid. This is because larger lattice energy means stronger electrostatic attraction between the positively and negatively charged ions. As a result, more energy will be needed to break the crystalline substance. That is, the compound would be stable. Melting and boiling point. Salts having high lattice energies will require more energy to break down the crystal. Consequently, melting and boiling point will be high. Solubilities of ionic solid. The magnitude of lattice energy of a solid gives an idea about the solubility of the substance's different solvents. Ionic compounds are generally soluble in water and other polar solvents, but insoluble in non-polar solvents such as carbon tetrachloride, benzene, etc. Solvation energy and solubility of ionic solids. When an ionic solid goes into solution, the strong forces of attraction between its ions are overcome and therefore its crystal lattice gets ruptured. But for this purpose, energy must be supplied. Now a question arises, how is the energy required to cause the rupture of the lattice obtained? The answer is not far to seek. When an ionic solid is added to the solvent, the cations and anions present in the solid are attracted by the opposite ends of the molecule. As a result, there is a strong interaction between the solvent and the ions, resulting in the solution of the ions. If water is the solvent, the process is called hydration, solvent, and the ions resulting in the solution of ions. The ionic solution or hydration is an exothermic process releasing a lot of energy. This is called solution energy. The amount of solution energy depends upon nature of the solvent. It is this energy which is utilized in causing rupture of the crystal lattice. The liquids which cause greater solution of ions and release large solution energy are good solvents for ionic solid. They have generally high dielectric constants. Thus water, liquid, ammonia, hydrogen, fluoride, etc. are good solvents. On the other hand, liquids with low dielectric constants such as benzene, carbon tetrachloride, etc. do not solvate the ions and therefore their solution energy is small. These are not good solvents for ionic solids. The process of ionization in water and then going in solution state has already been shown for NaCl in figure 2. The water molecules act as dipoles having positive and negative ends. The opposite ends of water dipole surrounds the cations and anions. The amount of energy released due to this interaction is sufficient to overcome the lattice energy of the crystal. Therefore, NaCl dissolves in water. In general, for a solid to dissolve in a particular solvent, its solution energy should be greater than lattice energy of the solid. The salts of alkaline earth metal Mg, Ca, Ba, etc. with polyvalent anions such as sulfate, oxalate and phosphate, etc. are much less soluble than the corresponding salts of alkali metals. This has been attributed to their higher lattice energies. The energy released in the solution of the ions is not sufficiently large to break their crystal lattice to an appreciable extent. Reason for low solubilities of silver halides. We know that a compound is soluble if the solution energy is more than the lattice energy of the compound. The low solubility of compounds like calcium oxalate, barium sulfate, lead sulfate, etc. in water are explained on the basis of their high lattice energies. In these cases, the lattice energies are so high that the solution energy released is not sufficient to overcome the lattice energy. However, the low solubilities of silver halides AgCl, AgBr, AgI in water cannot be explained on the same basis. The lattice energies of these compounds are almost the same order as those of the alkali metal halides, which are highly soluble. The unusual behavior of silver halides can be explained on the basis of outer electronic configuration of silver. The outer electronic configuration of Ag positive is 4D105S05P0. The electronic configuration of alkali metal ions Li positive, Na positive, K positive is noble gas NH0. The d electrons screen the nuclear charge from the outer electron less effectively than S and P electrons because of their poor penetration. Therefore, the effective nuclear charge experienced by Ag positive ion is much more than effective nuclear charge in alkali metal ions. Covalent character in ionic compounds. Ionic and covalent bonds are two extreme theoretical types of bond. In fact, most of the heteronuclear bonds have intermediate character. Even in this case of pure ionic compound, there is some degree of covalent character. When two oppositely charged ions, A positive and B negative, are brought together, the positive ion attracts the outermost electron of the negative ion. This results in distortion of electron cloud around the anion towards the cation. This distortion of electron cloud of the negative ion by the positive ion is called polarization. If the polarization is small, the bond is mainly ionic. On the other hand, if the degree of polarization is large, electron cloud is drawn more from the negative ion to the positive ion. Consequently, the charges of the ions become less, negative become less, positive charge also become less, because some of it is neutralized by the electron cloud of an ion. This decreases the ionic character of the bond and favors the covalent character. The polarization of an ion by cation is shown in figure 36. In figure 36, the two ions are shown without any polarization, assuming that the bond is completely ionic. This represents an ideal ion pair. The positive ion polarizes the negative ion and draws electron towards itself. As a result of polarization, there is decrease of positive charge on the cation and decrease of negative charge on the anion. This leads to covalent character. Obviously, if polarization is more, larger will be the covalent character of the bond. Thus, the type of bond depends upon the degree of polarization. If there is no polarization, the bond is mainly ionic. If the degree of polarization is small, the bond will be ionic with some covalent character, and if the polarization is more, the covalent character becomes predominant. The extent of polarization depends on both the ions. As power of cation is distort, power of cation to distort the or polarize the anion, the susceptibility of the anion to get polarized by the cation. The tendency of the cation to polarize and the polarizability of the anion are summarized in the following rules known as Fazan's rule. Fazan's rule. According to Fazan's rule, the polarization will increase by the following factor: small size of the cation. Smaller the size of the cation, greater is its polarizing power. The polarizing power of cation decreases with increase in its size. The small size cation have high electron density and therefore they tend to distort or polarize the electron cloud of the anion to greater extent. This can be easily illustrated by taking the example of metal fluoride of group 2A as given in table 4. Cation Be2 positive, radius in angstrom 0.31, melting point 678. Magnesium 2 positive, radius 0.65 in angstrom 985, melting point, and so on. In the table, the ionic size increases from beryllium 2 positive to Ba2 positive, same positive charge. Therefore, their polarization power decreases. As a result, the covalent character decreases or the ionic character increases. Consequently, the melting point of the halides also increase. In other words, the low melting point of BeCl2 in comparison to other alkaline earth metal halide is mainly due to its more covalent character. Larger size of the anion. The polarizability of anion increases with increase in size of the anion. This is obvious because the electron cloud in the bigger ion will be held less firmly by its nucleus and therefore would be more easily deformed towards the cation. Thus, larger the anion, the higher will be its polarizability and more will be its covalent character in its compound. Therefore, the anions like I-, Br-, S2-, Se2-, etc. are easily polarizable and have greater tendency to induce covalent character in ionic compound. In table 5, effect of increasing size of anion on the polarizability and melting point of ionic compound. Anions F-, Cl-, Br-, I-, their radius in angstrom 1.36, 1.81, 1.95, 2.16 respectively. The melting point 1268, 1073, 1023, 924. High charge on cation or anion. The polarizing power of a cation and polarizability of an anion increases with increase in charge of the ion. The highly charged cation will exert greater effect in polarizing anion and the highly charged anion will be more easily polarized. This can be easily illustrated by the following example. Na positive and Ca2 positive are almost similar ionic radii, but CaCl2 has higher covalent character than NaCl because of high charge of Ca2 positive. Consequently, the melting point of CaCl2 is less than NaCl. Electronic configuration of the cation. Cation with 18 electrons shell configuration known as inert or pseudo-inert configuration cause greater polarization than the cation with 8 electrons shelf configuration with the same size and charge. This is due to the fact that in case of 18 electron shell ion, there are 10 d electrons in addition to 8 s and p electrons. The d electrons do not shield the nuclear charge effectively and therefore they have increased effective nuclear charge. Consequently, these ions behave as though these were under the influence of greater nuclear charge and distort the anion to a greater extent. For example, if we compare the ions of same size, Na positive and Cu positive, Na positive has 8 electron shell configuration 2s2 2p6, while Cu positive has 18 electron shell configuration 3s2 3p6 3d10. The Cu2 positive ion polarizes the anion to greater extent than Na positive ion. As a result, the copper halide CuCl is slightly covalent and therefore insoluble in water, whereas NaCl is ionic and highly soluble in water. Melting point of CuCl is 705 Kelvin and that of NaCl is 1073. Similarly, Ca2 positive and Ag2 positive have almost similar ionic radii, but Ag2 positive has 18 electron shell 4f14 5s2 5p2 6d10, whereas Ca2 positive has 8 electron shell 3s2 3p6. These are the valence shell. Therefore, Ag2 positive is more polarizing than Ca2 positive and its compound are more covalent. For example, melting point of AgCl2 is 549 Kelvin while that of CaCl2 is 1065 Kelvin. We have already explained the low solubilities of silver halides in water in comparison to sodium halides. The silver halides acquire covalent character because of greater polarizing power of AgCl. Thus, according to Fazan's rule, the covalent character will be favored by small size of cation, large size of anion, high charge of cation and anion, the cation having 18 electron shell. So this was an end to the theoretical concept of all the points in ionic solid. After that, we will be discussing some of the questions which are asked in university exams. So, first question. In a close packed array of n spheres, how many octahedral and tetrahedral holes are present? Number of octahedral and tetrahedral holes in close packed array of 9 spheres, octahedral n, tetrahedral 2n. List the basic differences between NaCl and CaCl structure. The main differences are: the anions Cl minus ion have CCP arrangement. The anions Cl minus ions have simple cubic arrangement. The cations Ca2 positive ions occupy octahedral sites. The cations Cs positive ions are in the body center of the cube, that is occupy cubic sites. The coordination number of cation and anion is 6:6. The coordination number of cation and anion is 8:8. Select the correct choice. No reasons. Which of the two, MgO and CaO, is more hard? The answer is MgO. Which of the two, HCl and HBr, has larger ionic character? HCl. Which of the two, NaF and NaBr, has smaller melting point? NaBr. Which of the two, NaF and Kf, has larger lattice energy? NaF. Which of the two, NaCl or CaCl, has higher coordination number of Cl? CsCl. This question was asked in GNDU in 2017. Explain why melting point of NaCl is higher than that of AlCl3. Melting point of NaCl is higher than that of AlCl3 because of strong bonding forces with high lattice energy. On the other hand, AlCl3 is covalent compound with lesser forces of attraction and weaker lattice. Silver halides have low solubility in water. Explain. Silver halides are least soluble in water, though their lattice energies are almost of the same order as that of highly soluble alkali metal halides. This can be explained on the basis of the outer electronic configuration of silver ion. Its electronic configuration is Ag positive 4d10 5s0 5p0. The electronic configuration of alkali metals and Li positive, Na positive or K positive, Na0. We know that d electrons screen the nuclear charges from the outer electrons less effectively than s and d electrons because of their poor penetration. Therefore, the effective nuclear charge experienced by Ag positive ion is much more than effective nuclear charge in alkali metal ions. Due to greater nuclear charge, the Ag positive undergoes greater polarization and hence undergoes appreciable change from pure ionic character to covalent character. Question number 6. NaCl and BeO have same internuclear distance, but BeO has higher melting point than NaCl. Explain. BeO has double charged ions Be2 positive and O2 minus, and therefore they have stronger inter-ionic attraction between them in comparison to attraction between singly charged Na positive and Cl minus ion. As a result, the melting point of BeO is more than NaCl. Anhydrous AlCl3 is covalent, but AlCl3.6 H2 is ionic in nature. How do you account for this? Anhydrous AlCl3 is covalent, while AlCl3.6 H2 is ionic in nature. The third ionization energy of aluminium is very high. Therefore, large amount of energy is needed to convert Al atom into Al3 positive. Therefore, aluminium refers to form covalent bond with chlorine atoms, forming covalent AlCl3. Therefore, however, when dissolved in water, it undergoes hydration liberating hydration energy. The hydration energy released provides energy for the removal of 3 electrons from aluminum atom. In fact, aluminum does not exist as simple aluminum ion Al3 positive, but in the form of complex ion AlH2O6 whole 3 positive. Thus hydrated aluminum chloride is ionic in nature. Cu positive and Na positive are of same size, but CuCl is insoluble while NaCl is soluble in water. Explain. This question was asked in Punjab University in the year 2000, Maharishi Dayanand University in the year 2000, Chaudhry Devilal University in the year 2012. In NaCl, the hydration energy is sufficient to overcome the lattice energy of ionic NaCl. Hence, NaCl is soluble in water. The high hydration energy of NaCl is because of relatively high ionic character of NaCl, with the result that water dipoles interact strongly with Na positive and Cl positive ions. On the other hand, CuCl has sufficiently covalent character because of greater polarization of Cu positive ion. As a result of covalent character, its hydration energy is low and it's not sufficient to overcome the lattice energy of CuCl. Consequently, it is insoluble in water. Explain the following. LiCl has higher boiling point than HCl. LiCl is an ionic compound while HCl is a covalent compound. Therefore, LiCl has higher boiling point than HCl because of strong electrostatic force of attraction between the ions. This was asked in HPU in the year 2012. In which semiconductor the conductivity is due to movement of holes and electrons? Metal deficient with cation vacancies. In this kind of semiconductor, conductivity is due to movement of holes, and in metal excess defect with anion vacancies, conductivity is due to movement of electrons. In which stoichiometric defect, density remains same. In Frankel defect, density decreases. In Schottky defect. What is the coordination number of Na in NaCl 6, Ca in CaF2 8? These questions were asked in MDU in the year 2012. What is the coordination number of Ca2 positive and F minus ion in calcium fluoride structure? Coordination number Ca2 positive is 8 and F minus is 4. This was asked in GNDU University in the year 2018. So after that, there are some objective questions to which students are recommended to answer on their own. So yeah, that was all for today's video. Thank you all for watching and subscribe my channel for more such videos.